In 13.3, we're going to look at spanning tree algorithms. If we have a simple graph G, then a spanning tree is a subgraph forming a tree that contains every vertex of G. And a simple graph is connected if and only if it has a spanning tree. In this example, we just need, again, a tree subgraph that's going to connect with every vertex. So we could do something like this. We've got a tree, we have no cycles. There are other options as well. So for instance, we could go over here and come down, go over here, branch off there, branch there. We just need to not have any cycles in the graph. A minimum spanning tree in a connected weighted graph is a spanning tree that has the smallest possible sum of weights of its edges. Now, based on one of our earlier theorems, a tree is always going to have n-1 edges. So if they're not weighted, then there's nothing else that we can do. We can't reduce the number of edges needed to span the graph. But if we have weighted edges, then there are algorithms that will allow us to determine the minimum sum for all of the edges. The first algorithm that we're going to look at is called Kruskal's algorithm. In Kruskal's algorithm, we're going to start by focusing on the weights of the edges and let the tree sort of be formed by that. We're not going to have a tree necessarily during the process, but we'll end up with a tree at the end. So we're going to start with any minimum weight edge and its endpoints in G. So here, looking at the edges in this example, we have several of weight 1, and I can choose any of those as the starting edge. I'm going to go ahead and use AB here. I could have also used AE, CD, DH, those are all weight 1, and those all would have been fine as a starting edge. So I'll go ahead and record these and their weight as we add them to our tree. I'm just going to write the names of the vertices there. I'm not going to try to put the set notation on that. And then we're going to loop through until we have our n-1 edges in the tree. We're going to look for any edge in G with smallest weight that's not going to form a simple circuit in T if we add it to T. So we're not going to worry about that edge being incident with one of the vertices that's already in the tree. We're just going to look for another minimum weight edge and just make sure that we're not going to form any cycles, any simple circuits when we add them to our spanning tree. So for instance here, I have all those other weight 1 edges available to me. I could go ahead and add AE if I want to, but CD is also fine, doesn't have to be connected, and DH would have also been okay. And then we're going to continue going through and adding weight 1 edges as long as we're not forming a cycle. So maybe I'll add AE in next and then DH. I can put in both of those. I'm not forming a cycle in what's going to turn into my spanning tree. And we have no more weight 1 edges left available to us, so now we're going to turn to weight 2 edges and start adding those. So looking at all of the weight 2 edges, there are quite a few that I can choose from, but maybe I'll go ahead and use AM here around that side. And then we'll add in, say, NO. Again, it doesn't have to be connected to what we already have. And just keep finding weight 2 edges, so E to F. G to H. I'm not forming any cycles here, so those are okay to add. Then we'll keep going through that. M to N, we can add that one in. That's not going to cause any cycles. We can do, let's see, M to P, and then P and D. Those will also work. We've got another weight 2 edge here from E to I, so we'll add that one in. And then I can't add this weight 2 edge between B and C, and I also can't add the weight 2 edge between A and D with the other choices that I've made, because those would create a cycle in my tree, and I can't have a cycle in a tree. But there's one more weight 2 edge, so this one between L and P. I overlooked that one, so we can put that one in. That's fine. Not going to create a cycle there. And that takes care of all of the weight 2 edges that we're allowed to use. So now we're going to turn our attention to weight 3 edges and start going through and seeing which of those we can add. So I can't add this weight 3 edge between F and G. I can't add the one between B and F or the one between C and D, because those are all going to create cycles. Also H to L, I can't add that weight 3 edge. That's going to create a cycle. I to M, O to P, those are all going to cause problems. I can add this weight 3 edge between O and K, or the one between K and L. I'm not going to use both of those, but I can have one of them in there. Let's go ahead and do the KO edge. And then we're going to come over here. We've got these 2 weight 3 edges that could be added. So F to J or I to J. I'll choose I to J, use that one. And if we go through and count, and we can also see now that we have spanned all of the vertices. So this is going to give us a spanning tree. The number of edges that we've added should be equal to 1 less than the number of vertices. And if we tally all of these up, we're going to get a total weight here of 28. Now this answer isn't unique. You could have made different choices along the way. We talked about some of those, but whatever choices you make, still following the conditions set forth in the algorithm, you should end up with a weight 28 spanning tree from that. The other algorithm that we're going to look at, which will also generate a minimum weight spanning tree, we're going to use the same graph as our example, so we know that we should be getting a weight 28 tree at the end. This one's called Prim's algorithm, and it's going to focus on, instead of grabbing up as many minimum weight edges as it can and not worrying about the connectedness, it's going to try to add to the existing tree while not increasing the weight more than is necessary. So we're going to start with any minimum weight edge. I'll go ahead and use AB like we did before. We'll start keeping track of these. But then as we continue through the process, we're going to always add an edge of minimum weight that's incident to a vertex that's already in the tree T that we're forming, as long as it doesn't form a simple circuit when we add it to T. Otherwise, we're not going to have a tree anymore. So looking at what we have here, I need edges incident with either A or B. So we've got this edge from B to C of weight 2. Well, I'm not going to use that yet because I've got this edge here from A and E of weight 1. And that's the minimum weight edge that's available. So we only have one choice of an edge to add at this point, given that we started with the AB edge. And that was the wrong weight for AB. That should have been 1 instead. And then we're going to look at all of the edges, again, incident with vertices here. I don't have any weight 1 edges incident, but I do have some weight 2 edges. So I can use either the EI edge, the BC edge is now available, A to M, and A to D. Those are all weight 2. Any of them are fine. I'm going to go ahead and use the A to D edge. And once we do that, we now have these weight 1 edges incident to D. D is now in our graph. Everything else out here is weight 2 or 3. So I now need to add either CD or DH next. And then I can still add the other one without forming a tree. So both of those are going to come next in our order. And we'll continue on from here, looking at all of our weights. We don't have any weight 1 edges remaining. We do have weight 2 edges that are incident with vertices in our graph. So for instance, we could use this A to M edge of weight 2. That's not going to cause any cycles. I could go from D down to P. That's not going to cause any cycles. Those are both weight 2. Looking at this, I can't add the MP edge because that's going to create a cycle. I could add the EF edge, that's a weight 2. That's incident with a vertex already in our tree, and the H and G edge. That one's fine. We could go E and I here. That's another weight 2. We have some other weight 2 edges, so L and P right there. And That's it for weight 2 that are, oh no, we've got M and N right there. That's not going to cause a cycle. N to O, I can add that in without creating a cycle. So we have all of those weight 2 edges. And that is everything. So again, the BC is going to cause a cycle, and M going to P is also going to create a cycle. So I can't add those. So we'll turn our attention now to weight 3 edges, again, incident to any of our existing vertices. So I have F to J, that's an option. I to J is also an option. I can't add HL. I can add LK or OK. I can't add the OP edge there. So let's do L to K and then I to J. And that is going to complete our process. We'll now have n-1 total edges that we've added. So we should have a tree. And add up all those weights, assuming I wrote them all down correctly and didn't miss one, we should end up with a total weight of 28. So we'll get a different answer, possibly, than we did with Kruskal's algorithm, although you could end up with the same final tree, but that's not necessarily going to be the case, and depending on which choices you make along the way, you could have ended up with a different spanning tree than the one that I have here, but the weight should still be equal to 28. So these algorithms are just going to find a minimum weight spanning tree. It's not going to give us a way of finding all of them.